Functions, Lesson 3, Composite Functions. So we're going to start off by recapping the definition of a composite function and then revising how we can create composite functions. So a composite function is created when we apply one function and then apply another function afterwards, a little bit like a combination of transformations. So an example could be something like this: f g of x. This is a composite function. It tells us that functions f and g are being applied, and the order in which we write the letters matters. Because g is closest to x, this composite function is created by applying g first and then f second. So let's work out what the overall effect of applying this pair of functions in this particular order is. So fg of x means we're applying f to g of x, which means we're applying f to x plus 4, because g of x tells us we get x plus 4. Now let's look at the function f. In words, that simply says square the input. F of x equals x squared means you're squaring whatever is in the brackets. So if we're applying f to x plus 4, that means we're squaring our input, which means we have x plus 4 all squared as our outcome. And this is the composite function, which makes sense. We're starting with x, we're applying g, which gives us x plus 4, and then we're applying f, which tells us to square what we've got, which gives us x plus 4 squared. Remember, the function g in words is add 4, the function f, if we express it in words, means square. And we've created a composite function as a result. Let's look at this composite function in the other order. So rather than fgx, let's look at what happens if we create the composite function gf of x. Now again, the function that is closest to x is first, so this means we need to apply f first. We then apply g second. So let's work this through. So this is g of f of x. So f of x happens and then we apply g, which means g is going to be applied to x squared. The function g tells us in words that we need to add 4 to whatever our input is. Our input is now x squared, so we're replacing the x in g of x with x squared, which gives us x squared plus 4 as an outcome. So this time we started with x, we applied the function f, which tells us to square whatever the input is, which gives us x squared. We then apply the function g, which tells us to add 4 to whatever our input is, which gives us x squared plus 4. And we have our composite function. So notice fg of x is equal to x plus 4 all squared, and gf of x is equal to x squared plus 4. So order matters. Think about this logically, it makes sense, it links back to everything you've ever learned about the order of operations. If we apply the functions with g first and f second, you're adding 4 and then squaring. If we create a composite with f first and then g, you're squaring and then adding 4. And we know the order in which these operations happen matters. So in this particular example, we can clearly say that fg of x is not equal to gf of x. There may be instances where an overall composite function is the same, regardless of which order you do the functions in. For example, if your two functions simply involved adding and no other operations, then that would work. But in the majority of cases, fg of x will not be equal to gf of x. So make sure you understand the order in which the functions are being applied to create the composite function. It is always the function that is closest to x that occurs first. Let's have a look at a few more examples. So you sometimes see composite functions which look a little bit like this. So if we see f squared, that does not mean square the function f, it means apply f twice. And because it's the same function, there is no order to worry about here. So we're applying f to f of x. And let's work it through. So f of x is of course x squared. So applying f once gives us x squared. Then remember what f tells us to do in words. It tells us to square whatever your input is. So our input is now x squared, which has got to be squared again. So we have x squared all squared, which gives us an answer of x to the power of 4. Let's have a look at the function g squared of x, which of course means g of x, which means we're applying g to g of x. We're applying g of x first and then applying g again, which means we're applying g to x plus 4. And then let's remind ourselves of what the function g of x tells us to do. It simply says add 4 to your input. So if your input is now x plus 4, if we apply g to it, all we're doing is adding another 4. So we're replacing the x in g of x with an x plus 4. And that gives us an answer of x plus 8. Composite functions can be made up of 3 functions. So we could have a composite f, g, h of x. And of course the order here has got to be h first, then g, and then finally f, as we're working our way outwards from the function which is closest to x. H is closest, so it occurs first, g is second closest, so it occurs second, and f is the furthest away, so it is applied last. So we want to leave the f and g for the moment and think about h of x, first of all. So h of x is equal to 2x. So that gets us to this stage here. We're then going to leave f for the moment and we're going to focus on this part, g of 2x. So thinking about the function g of x, it simply means add 4 to whatever your input is. Our input is 2x, so we get 2x plus 4. And then finally, we're applying f, which tells us we need to square whatever the input is. The input is, of course, 2x plus 4. So we have 2x plus 4 all squared, which if you want, you can expand it, but there is actually no reason for us to do that. So, having had a look at these worked examples, setting your steps of working out very clearly and carefully, you're going to have a look at these 7 composite functions and find out what they are. The answers will come up in a minute, so you will want to pause and make sure you try the questions yourself first of all. So you can see the answers on the right-hand side here. Don't forget to simplify fractions wherever possible. And just a quick word about question 7. We start off by applying the function p. Which gives us 10 over x. And then we have to apply p to this again, which means 10 divided by the input. And of course the input is this. So that means we have to do 10 divided by 10 over x, which is 10 over 1 multiplied by x over 10, which gives us an answer of x, just in case you weren't sure. And it's quite interesting that when you apply p to x and then apply p again, you get back to x. So we have a system which looks a little bit like this. And this will relate a little bit later on to the topic of inverse functions, which you will be looking at afterwards. So we're now going to extend our understanding of composite functions to thinking about the domain and the range of a composite function. We're going to start off by looking at this example, and we're going to create the composite function g(f) of x. So you can see we have the function f of x and we have the function g of x. Let's look at the combination of these two. So order, g(f) of x means that we apply f first and then g. So that's g of f of x which is g applied to x squared plus 5. And of course the function g, if you look at it in words, 2 lots of x or 2 lots of the input, it means simply multiply your input by 2. So we have 2 bracket x squared plus 5, which we could expand if we wanted to. We're going to sketch each of these stages of the transformation that's occurring. So let's sketch the graph of y equals f of x, first of all, or x squared plus 5. This is a simple parabola. It crosses the y-axis at 0, 5. And we're then going to apply the function g to this. So the function g tells us we need to create a stretch in the y direction with a scale factor of 2. So all the y coordinates will double, the x coordinates will remain the same, and we will end up with a parabola that looks like this, with a y-intercept of 10. So this is our graph of y equals g(f) of x, which is the graph of 2 bracket x squared plus 5, or 2x squared plus 10, and you can then clearly see its y-intercept of 10. So let's have a look at the information step by step. The function y equals f of x has a domain of x is a real number. Its range is y is greater than or equal to 5, or f of x is greater than or equal to 5. Now, g then acts on f of x. So the domain of g(f) of x is x can be any real number. But the range of g(f) of x is y is greater than or equal to 10. So the function g(f) of x, which is 2 lots of x squared plus 5, has a domain which is x is any real number, and we can see that. Look at the fact that g is acting on this function here. And the full x-axis is allowed, but the range at the very end, if we look at this, the y-coordinates can only be 10 or upwards. So we have the following information. So let's look at this a little bit more carefully. We start with x. The function f is then applied, which transforms x to f of x. The function g is then applied, which takes us to g(f) of x. So f acts on the values in its domain, which takes us to its range. G then acts on the range of f of x, i.e. the range of f of x becomes the domain on which g of x now acts, which of course then results in g f of x. So let's have a look at this with a diagrammatic approach. Let's imagine that this shape represents the domain of f. And if the function f is then applied to this domain, it will take us to the range of f, which we'll shade in the same colour. Now, in order for our composite function to be created, the function g has then got to be applied, in this particular case, after the function f. So the domain of g has got to be the same as the range of f, or it's got to include the range of f. So I'm going to shade this in, and this will represent the domain of g. Now, if we were simply applying the function g, that would take us from the domain of g to the range of g. Like that. But what actually we're doing is applying the function gf, so f first and then g, the composite function gf of x, which means that we start with the domain of f because f is being applied first, and we end up at the range of gf of x. So just to reiterate that again, the function f acts on its own domain, taking us to its own range. The function g is then applied to effectively its domain, and that domain must contain the range of f, or it must be equivalent to the range of f. The function g, if it acts on its whole domain, would take us to its entire range. But actually, we're only applying the g function to the range of f, which means that the overall range of gf, the composite, will be contained within the range of g. It may end up being the same as the range of g, but it's definitely going to be contained within that range of g. So if we apply this to the example that we have just seen, the domain of f of x, which was equal to x squared plus 5, was x is any real number. And this was then mapped to a range of y is greater than or equal to 5. Remember the parabola with a y-intercept of 5. The function g of x, completely independently of f of x, had a domain which was also the set of real numbers. And when you apply g of x to this particular domain, you can create any y value. Think about it. The function g says double your x value. If you can have any x value and you double it, you can create any y value. So the range for g, completely independently of anything to do with f, is that y is any real number. But when we create this composite function, g f of x, that means the function f has been applied first of all, and then the function g is being applied. So the original domain will be the same as the domain of f, the first function to be applied. The range is then whatever the final outcome is, which is 10. Y is greater than or equal to 10. Or, if you want to, you can say g f of x is greater than or equal to 10. So you can see that this applies very carefully to the example above we've got in the diagrammatic form. We start with this domain here, x is any real number, and we end up with the range of values for f, which is that y is greater than or equal to 5. You can see that this is contained within the overall domain of g, so the range of f, which is y is greater than or equal to 5, falls within the domain of g, which is x is any real number. We then apply the function g to create the composite, and we end up with y values which are greater than or equal to 10, and you can see that this falls inside the range for g on its own independently. So this does match the diagram that we've drawn above. So to finish off with one final example, we're going to have a look at a composite function which this time is created as fg of x, which of course means g is being applied first, f is being applied second. So this tells us we have f of g of x, which means we're applying f to 2x. The function f, if we think about it in words, tells us to square and then add 5. So we take our input, which is 2x, we square it and we add 5, which gives us 2x all squared plus 5, which gives us a final outcome of 4x squared plus 5. So let's now think about domains and ranges. So we start with x. The function g is applied first of all, and we start with the domain x is any real number. Applying g takes us to g of x, and of course if you apply g first of all, the range of g is simply going to be y is any real number. The function f is then applied, which takes us to the composite fg of x. And if we look at the function f, it's saying square your input and add 5. Well, that means that we're going to end up with y values which are greater than or equal to 5. And we can see this from the overall sketch diagram of the composite function as well. It's a graph of 4x squared plus 5, which is a parabola, with a y-intercept of 5. So you can very, very clearly see the range of the composite function. It's y values of 5 or above only. So the domain of the composite function, fg of x is any real number, because this is the domain of g, the first function to be applied, and the range is simply y is greater than or equal to 5.